Okay. That's better. Okay, let's do that. Let's find the exact area under the curve y equals e to the x between x equals 0 and x equals 2. You don't need a picture here. I'll draw one anyway. That area. So in other words, what I'm asking you to do here is evaluate the definite integral between x equals 0 and x equals 2 of e to the x dx. We're not going to go through all the trouble of breaking the interval 0, 2 up into n parts and constructing those rectangles and computing the area of the rectangles and adding them all up and letting the number of rectangles go to infinity. Instead, what we're going to do is use the fundamental theorem of calculus. So we're looking for an antiderivative of e to the x. We're going to plug in x equals 0 and x equals 2. So we'll plug x equals 2 in, subtract off, we get x equals what we get when we plug x equals 0 in. What is the antiderivative? What is an antiderivative of e to the x?
E to the
function. Oh, sorry, say it again.
It's just e to the x.
Exactly, it's just e to the x. Antiderivative of e to the x is just e to the x. And so all we have to do is plug in this number for x and then subtract off what we get. We plug in that number for x. So this is just e squared minus e to the 0. In other words, e squared minus e to the 0 is 1. And there we go. Fundamental theorem of calculus saves us so much work. Let's do another problem. Find the area enclosed between the curve y equals 1 minus x squared and the x-axis. This was a little bit more involved than the previous question, the question I gave you today and the question we did at the end of last class, because I didn't say between x equals something and x equals something else. Instead, we're going to have to use some information about the curve to come up with those two values, the ones we're going to put here and here. Let's go ahead and figure out what this curve looks like. Maybe it's already obvious to you. I think if I were writing this, I would write it as y equals minus x squared plus 1. Just put this term second and this term first, because it makes it obvious what it is we're looking at. What shape is this curve? Y equals negative x squared plus 1. What kind of curve is that?
It's an upside down parabola moved up
Exactly.
one.
It's you answered both the questions. Yeah, it's an upside down parabola. You can see the number in front of the x squared is minus. We know that if we have a second degree polynomial, which this is, largest degree of x is 2, it's going to be a parabola. We can see the number in front is a minus x is minus, so it's going to be an upside down parabola. You were about to say something else?
The plus 1 moves it up 1.
The plus 1 moves it up one. Exactly. So we know that this is a parabola flipped upside down, and the plus 1 moves it up 1. So kind of right away, we know it looks like that. Y equals 1 minus x squared, or minus x squared plus 1, doesn't really matter. However you want to think about it, crosses the y-axis at 1. Let's figure out where, so clearly what we want is this area right here. All we need to do is figure out where it crosses the x-axis. So let's go ahead and find our x-intercepts. We do that the usual way. We'll set y equals 0. So minus x squared plus 1 equals 0. In other words, x squared equals, all right, I'll multiply both sides by negative 1. X squared minus 1 equals 0. That factors as x plus 1 times x minus 1 equals 0. All old stuff, all the pre-calculus stuff that we reviewed at the beginning of the course. And here, x equals minus 1 or x equals 1. So it crosses the x-axis at minus 1 and 1. Now we do know these two numbers. So we're just integrating from negative 1 to 1. You can write it like this. You can write it like this. I don't care. It doesn't matter at all. I'll write it like it was originally. 1 minus x squared. All we need is an antiderivative for 1 minus x squared. What's an antiderivative for 1? Something you can take the derivative of and get 1.
1x.
Exactly, 1 times x. And then we can use the antiderivative power rule on that. Here we have n equals 2, so it's 1 over 2 plus 1, 1/3 x cubed. Remember you're going antiderivative here, not derivative. We're going backwards. So this is equal to, if I plug the 1 in, I end up with 1 minus 1/3 times 1 cubed. If I plug the negative 1 in, I end up with negative 1 minus 1/3 times negative 1 cubed. And now it's just a matter of keeping the plus signs and the minus signs, right? If you want to pull out your calculator at this point, fine. So I'm just going to finish it up here. So 1 minus 1/3, that's 2/3 minus negative 1 minus, and 3 more minuses, so plus 1/3, so that's minus negative 2/3. So 2/3 minus negative 2/3 is 2/3 plus 2/3, or 4/3. So the area of this region over here is 1 1/3. The calculus was a piece of cake. If anything was difficult in this question, I don't know if it would be difficult, but it was a little bit of pre-calculus, a little bit of functions, and strangely, arithmetic can be more troublesome than you might think. Keeping minus signs straight, that sort of thing. Let's do some more just definite integrals out of the box. How about the integral from 1 to 2 of one over x? So without, working very hard, you can put the brackets down, you can put the 1 here and the 2 there. All we need now is an antiderivative for 1 over x. And what is a good antiderivative for 1 over x?
Would it be the natural log of x?
Exactly, the natural log of x. And this just means take this number, put it in for x, subtract off what you get when you take this number, put it in for x. So natural log of 2 minus the natural log of 1. We can simplify that slightly. Or you can get a decimal value, it's fine. Natural log of 2 is just natural log of 2. I mean, you can work that out of your calculator if you like. Natural log of 1, we remember that's just the number 0. Natural log of 2 minus 0, or natural log of 2. Let's do another one. What's good? How about, oh, I know. How about the integral from -1 to 1 of x cubed minus x? Yeah, oh, dx. Antiderivative of x cubed using the antiderivative power rule, 1/4 x to the 4th. Antiderivative of x using the antiderivative power rule, that's really x to the 1. 1/2 x squared. So plug this number in for x in both places, subtract off what you get when you plug this number in for x in both places. So 1/4 times 1 to the 4th minus 1/2 times 1 squared minus 1/4 times -1 to the 4th minus 1/2 times -1 squared. So this 1 to the 4th, of course, is just 1. So this is 1/4 minus 1/2 minus 1 to the fourth, of course, is 1. 1/4 minus 1/2. I mean, you can work out the brackets, the parentheses if you want, but you see what you have here is exactly the same as what you have here, and so you're going to get 0. We've graphed a function that looks almost exactly like this several times. If you want to graph this, to sort of explain why you got 0, you can see it from the picture, even though the picture is not necessary. This function looks like this. It has, well, I don't know why I shaded that in. You don't need the shading. But that's sort of what we did over here. This function has symmetry around the origin using the language of your pre-calculus. It has odd symmetry. And so the stuff above the x-axis over here exactly cancels out the stuff below the x-axis over there. We know that stuff below the x-axis, as far as definite integrals go, counts as negative area. And so it's not surprising that we should get 0. Okay. I think that's good for now. Let's move on to another concept. I guess I can start over here. Let me put up a problem. Say the temperature in Lynchburg, so temperature T in Lynchburg should have uppercase L in degrees Fahrenheit, T hours after 9 a.m. is given by the following formula. Capital T, the temperature at time t, at little t, equals, let's say, let's be optimistic. 50 plus, actually, let's say after 10 a.m. 50 plus 5 t squared. Let's start with some easy questions. Find the temperature at 10 a.m. and at noon. So for 10 a.m., what's little t? So little t is the number of hours after 10 a.m. So what's little t at 10 a.m.?
0.
Right, 0. So for 10 a.m., t equals 0. 0 hours after 10 a.m. And so capital T of 0, according to the formula, the temperature at time 0, the temperature at 10 a.m. is equal to 50 plus 5 times 0 squared. Or 50 degrees Fahrenheit. And at noon, what's little t? How many hours after 10 a.m.?
2.
Right, it's 2 hours after 10 a.m. T2 equals 50 plus 5 times t squared. That's 50 plus 5 times 4. 50 plus 20 is a lovely 70 degrees Fahrenheit. Obviously, this can't be true forever because, you know, sometime in the very near future, if this continued to be true, it'd be well over 100 degrees in Lynchburg. That's probably not happening. Okay, so 50 degrees at 10 a.m., 70 degrees at noon. How about this? Sketch a graph of temperature versus time between 10 a.m. and noon. Sketch a graph of temperature versus time between 10 a.m. and noon. So I'll put lowercase t on this axis, that's t in hours, number of hours after 10 a.m., and I'll put uppercase T temperature on this axis, and this, of course, is in degrees Fahrenheit. And let's see, 50, 60, 70, 1 hour, 2 hours. For those of you that draw graphs in other classes, you might be used to putting like a little zigzag thing right here to indicate we're not going all the way down to 0. You can put that in if you want. So at time 0, I'm going to take that out. It's just making my picture look more complicated than it needs to be. At time 0, at 10 a.m., which is time 0, we're at 50 degrees. At time 2, we're at 7 degrees. Dot in some horizontal lines here with my own graph paper. Maybe some vertical lines too. So at time 2, we are at 70 degrees. And what shape does this graph have? Again,
Parabola.
it's a parabola. This time it's right side up because it's a positive number for the t squared. So it's a parabola stretched vertically by a factor of 5 and shifted up by 50. So it looks like, I mean, we could figure out where it is at time 1. If I put time 1 in here, I have 50 plus 5 times 1 squared, that's 55. So I'm at height 55 right here. It's a parabola. Looks like this. That is a pretty awful looking parabola. Try again. Okay. Could be worse. And then, of course, this is a graph of what I have over there. T equals 50 plus 5t squared, that parabola. Okay, now to some new stuff. I mean, nothing we've done so far requires anything more than pre-calculus. Is the average temperature in Lynchburg between 10 a.m. and noon. Right now, just looking at the picture, equal to 60 degrees? Or is it higher than that? Or lower? Average temperature in Lynchburg between 10 a.m. and noon. Is it 60 degrees? Or is it higher than that? Or is it lower than that? And what's your reasoning? Just looking at the picture and not, you don't have to put this in math speak. Just reason it out.
Is it less than 60?
I would agree with you. What's your reason?
Because I guess 1 would be the middle between 10 a.m. and noon, and that's below 60.
Yeah, I mean that's definitely getting close to it. I mean, really, it spends most of its time below 60 degrees, right? It's only above 60 degrees for like this last little bit. Does that make sense? So it spends. So I would say it's lower because it spends more time closer to 50 degrees than it does up near 70 degrees. Spends more time near 50 degrees than near 70 degrees. So the moral of this story in part C is that if you want the average value of a function over an interval, it's not as simple as just taking the value of the function at the beginning and the end and adding them up and dividing by 2. It's not this. You can't just take the beginning and the end and average them. Which of course begs the question of how do you find the average value of a function? So you can't find the average value of a function f, this time I called it t, I'll call it f over here, over an interval AB, in this picture 0 to 2, by averaging the value of f at the beginning and the end. Averaging the value of f at the beginning and end. Which of course raised the question, so how do we do it? So to find the average value of a function, this is what you do. It's 1 over the length of this interval, so in other words, b minus a, times the integral from a to b of f of x dx. So in other words, you take the total area under the curve and divide by the length of the interval. Total area under the curve divided by the length of the interval. So let's go ahead and do that in this case. I'm going to leave the graph, leave the formula, get rid of all this stuff. So find, where are we? D. Find the average temperature in Lynchburg between 10 a.m. 0 and noon equals 2. So using this formula over here, which isn't really much to memorize, total area under the curve divided by the length of the interval. The average temperature equals 1 over 2 minus 0 times the integral from 0 to 2, the area under the curve of this, 50 plus 5t squared. Now, instead of putting an x here, because our horizontal axis is not x, it's t. So I put dt. Whatever variable is here, use the same variable there. So this is equal to 1 over 2 times, let's go ahead and take the antiderivative. Antiderivative of 50 is going to be 50, this time not 50x, 50t, because our variable of integration is t, not x. And the antiderivative of 5t squared, we'll put the 5 down. We'll put 1 over 2 plus 1, so 5/3 t cubed. Just using our antiderivative power rule. And so this is 1/2. Okay, plug in our 2, so 50 times 2 plus 5/3 times 2 cubed minus 50 times 0 minus 5/3 times 0 cubed. A lot of parentheses there. So 1/2. 50 times 2 is 100. If you don't want to do all this arithmetic yourself, feel free to pull out your calculator. 2 cubed is 8 times 5 is 40. Minus 0. So that's equal to 50 plus 40 over 6, or which is the same as 50 plus 20 over 6. That's probably plus 20 over 3, I should say. In other words, about 56.7 degrees. And you see that just like what you said, the average temperature between 10 a.m. and noon is below 60 degrees, about 56 degrees. So average value of a function, you don't take the value of the function at the beginning of the interval and the value of the function at the end of the interval and add them up and divide by 2. You don't average them like that. Instead, you take the total area under the curve and divide by the length of the interval. Based on my past experience, it doesn't seem to matter how many times I say that. There'll be some people, hopefully not you, on the final exam who will still just take the value of the function at the beginning and the value of the function at the end and add them up and divide by 2. So assuming that there may be people that do that, don't let it be you. So use this instead. Is everybody okay with that? Is there anything I can explain? I think sometimes it's just the pressure of the moment and, okay, good. Okay. I'm going to assume it's okay. If you have some questions and you can't bring yourself to ask them right now, feel free to ask me during office hours. I'm happy to explain. But I think if you just remember this exists, it's not that hard to use. This is just the area under the curve, and then you just divide by the length of the interval. That's all there is to it. Okay, how are we doing? 9 minutes. Last section of the course. Believe it or not, even with one fewer week this semester, we still finished on time, and that is largely credit to you guys. I'm very impressed. So we will have some time. We won't polish this off today. We'll just start this today. We'll polish this off on Wednesday. The rest of Wednesday's class and Friday can all be reviewed for the final. I'll tell you everything about the final that I can, and hopefully you'll feel comfortable. That will, of course, be after the Thanksgiving break. So you'll have time to practice. If you need to get in touch with me to work on some skills, we can definitely do that too. Okay, so integration by substitution. Integration by substitution, antiderivative by substitution, this is basically just the chain rule backwards. And you don't need any fancy substitution in simple cases to be able to do this. For instance, let's say I asked you to find the antiderivative of something like one-third wait a second, I'm sorry. My bad. 3 sine squared x times cos x that looks at first glance like a horrible thing to have to take the antiderivative of. But remember, antidifferentiation is just differentiation backwards. So you want to ask yourself, what was the function that somebody took the derivative of to get that? Now, again, when you first look at that, it might not be obvious. Let me write this a slightly different way. 3 times sine x squared. Of course, when you put a square there, it just means that you put parentheses around the sign and squared it. Cos x dx. So this is the answer on somebody's page. That was the derivative of something. And if I tell you that to get this, the person used the chain rule, then you start looking at, oh, I have like an inside part of this function and an outside part of this function. And here, this is the derivative of that, the derivative of the inside part. Somebody really did use the chain rule to be able to come up with this derivative. So now it's unnatural to think backwards, but ask yourself, what was the original function? What was the original function that somebody took the derivative of using the chain rule to get that? This 3 and then the square up here, what does that come from?
A cubed function.
Yeah, it comes from something cubed. And what's the relationship between what goes in here and what goes in here?
It's the same.
It's the same. That's all there is to it. We're done. Let's just check. Let's take the derivative of sine x all cubed. Or if you like, sine cubed x. It's the same thing. Well, the 3 comes down. The 3 becomes a 2. We write the inside part exactly as it is. And then at the very end of the problem, you multiply by the derivative of the inside part. Derivative of sine x is cos x. That's what we started with. So we did it right. Let's just do one more. How about we take the antiderivative of cosine of x squared plus 5x plus 3, all that times 2x plus 5. So I'm not really teaching you integration by substitution yet. I'm just showing you the basic principle. So again, somebody took the derivative of something, they used the chain rule, and they ended up with this. You see, you look right away, you see, oh, 2x plus 5, that's just the derivative of x squared plus 5x plus 3. If I take the derivative of x squared plus 5x plus 3, I get that. And when you use the chain rule, the last thing you do is take the derivative of the inside part. So where did the cos come from? If somebody took the derivative of something and they ended up with cos, what was the original thing?
Sine.
Yeah, sine. And what's the relationship between this and what goes in here?
It's the same.
It's the same, yeah. X squared plus 5x plus 3. And then we'll put in our plus c. We can check this one. So the derivative of sine x squared plus 5x plus 3 plus a constant is equal to derivative of sine is cosine. We'll write the inside part exactly as it is. And then at the very end, you multiply by the derivative of the inside part. Chain rule backwards. That's all there is to it in a sense. The substitution or U substitution, which I haven't actually taught you yet, is just a bookkeeping way to make it feel less unnatural and so you can handle more complicated problems. That's all there is to it. We should be able to do that next time, I'm guessing in less than half an hour. And after that, we can start our review. And we can review for the rest of the semester. See you, everyone.
Thank you. Have a good day.
You too. My pleasure. Bye now.
Dr. Order,
Yeah.
I do have a question just about, so I'm kind of worried about, like, I'm not really sure how I'm doing in the class because, like, I saw the midterm grade, but I would like to see my other exams.
Yes.
To help me study for the final.
Absolutely. So I think I can get at least your first two midterms back to you before Friday, and the third midterm will hopefully appear this, within a week or so.
Okay.
Okay, so you should have everything. You already have all the grades on your already have all the grades on your homework. And of course you have the grade on your midterm, which includes the review test and midterm number 1. So I'll get all those back to you so you can see which mistakes you've made. And by, the first two by Friday and the third one sometime next week.
Is there anywhere that we can see, like, our homework grades too? Or?
I'm thinking about how I might be able to do that. I can certainly, you mean your individual homework grades?
Well, just like our average for our homework.
Yeah, absolutely. And I will also tell you which ones are missing and give you the chance to put those together before your final.
Okay. So if you give us back our exams, will you just like upload them to the shared drive?
That's what I'm going to do, because this semester, so last semester I did something different, but this semester I printed them out and graded them on the paper. So what I'll do is scan them and upload them.
Okay. All right. Thank you.
Sure.